Next we go to applications of exponential functions. This is part 2 of our brief study of exponential and logarithmic functions. And my name is NVCC. We will look at graphs, that's to say transformations of exponential functions, and equations and compound interest, just as it says here. Okay, so as for graphs, all of the usual transformations apply. Okay, so let's take an example that we have in the book. Problem 2.4.6 asks us to graph y is equal to 3 raised to the x plus 1. Now, we have defined exponential functions as any base raised to the x power, where not just any base, but a base greater than 0 and not equal to 1. But in fact, it doesn't have to be just the base raised to x alone. It could be the base raised to some function of x. It's not against the law, so why not? And we can have it multiplied by something and scale it. We can add or subtract something to it. We can move the thing left and right using all of the usual techniques. So let's start out here with what I call step 0. The foundation of this graph is y is equal to 3 to the x power. So I know that my graph goes through 0, 1, so I'm drawing that in place. It goes through the point 1, 3. It goes through the point 2, 9. It goes through the point -1, 1/3. How come? Well, 3 raised to the power 1 is 3. 3 raised to the power 2 is 9, etc. 3 raised to the power -1 is 1/3. So what I have on this graph is bits of y equals 3 to the x. Now, people who did pre-calc with me in the last semester know that what follows step 0, my foundation, is step 1, my first transformation. And that is 3 raised to the power x plus 1 in this case. What happens here? Well, f of x plus 1 is equal to f of x moved left 1 unit. Okay, so I have my step 0 here. I'm going to take all of the points that I know on that one and move them left 1 unit. So in particular, I have -1, 1 on this graph. I have -2, 1/3. I have 0, 3. I'm going to plow right through that to get to 1, 9, and so on. So I pick up my original graph and move it all left 1 unit. So this is real old school graphing. One more problem, because I like these so much. This one is problem 2.4.10. Y is equal to -2 plus 3 to the negative x. I'm going to skip step 0 here and draw 3 to the negative x. All of these have the same basic shape. I have a base greater than 1, and my exponent is negative x. If I add negative 2 to that, then it's no longer going to be asymptotic to 0 on the right. It's going to be asymptotic to negative 2. And it's no longer going to go through 0, 1. It's going to go through 0, negative 1. And this deserves another color. It's going to have the same basic shape, of course, but it's going to be the whole thing moved down 2 units. So this is not much of a surprise, it's just a pleasure. Our second topic is exponential equations. Now, these all rely on this fundamental fact. That if we have a given base with two different appearing exponents, then this equation, b to the power x equal to b to the power y, is true if and only if x is equal to y. So, problem 2.4.13 asks us to solve this equation. 2 raised to the power x is equal to 32. Well, what we need to recognize here is that 32 is equal to 2 to the 5th power. And now we could say with confidence x is equal to 5. That one's pretty straightforward. Here's one a bit less straightforward, number 19. Where we see 16 raised to the power x plus 3 is equal to 64 raised to the power 2x minus 5. Okay, these don't look so much alike. I know that there's a 16 is equal to 4 squared, and 64 is 4 times 16, which means that 64 is equal to 4 to the 3rd power. So what we really have in this equation is 4 squared raised to the power x plus 3 is equal to 4 cubed raised to the power 2x minus 5. Now I'm going to use rules of exponents to rewrite these equations. So I have 4 raised to the power 2 times x plus 3 is equal to 4 raised to the power 3 times 2x minus 5. Okay. So, in order for this to be true, it must be true that 2 times x plus 3 is equal to 3 times 2x minus 5. So 2x plus 6 is equal to 6x minus 15. So I'm going to move the 2x to the right side and the 15 to the left side, and what do I get? 21 is equal to 4x. So it says here that x is equal to 21 over 4. Okay, now I need my calculator. I don't suppose it would be impossible for me to check this by hand, but on the other hand I don't particularly want to. So I come back to my calculator, clear out what was there before, and I know that x is supposed to be equal to 21 over 4. So I'm going to take that 21 divided by 4 and store it using this button here in the variable x, like so. So if I forget what x is, I say, yo, what's x? There it is, 5 1/4. Okay, so we had 16 raised to the power x plus 3. Raised to the power x plus 3. And I get that colossal number, which I don't think I've ever even seen before. And then the other problem was, the other side of the equation was 64 raised to the power of 2 times the same x minus 5. So note, I am not finding for myself 2x minus 5. I go back to this original form of the problem because I want to make sure that those two are actually equal. I press enter and wow, I get the same never before seen number again. So this shows that I solved the equation correctly. So our next and last application is about compound interest. So we had two different equations for this. The more important of them being not that, but rather that our future amount, which we call A, is equal to the beginning amount times our little friend E raised to the power of this product, the interest rate, as in 5%, 7%, etc., times some number of period, typically years. And we also talked about this as future value on the left side of the equation is equal to the present value times E raised to the power RT. So I should note that this equation applies only to continuous compounding. We had another one that said that the amount that we have in the future is equal to the amount that we start with times 1 plus the rate divided by the number of compounding periods, for instance 12 in a year or 365 in a year, raised to the power n, the number of compounding periods in a year, and so many years. So let's look at a simple example here. We will compare a certain amount invested in both of these cases for a certain number of years. So let the principal be $10,000. and let the time be 20 years. And let's let the rate be equal to 5%. Okay, so in the continuous case, our equation is the future value is equal to 10,000 times 1 plus, my bad, 10,000 times e raised to the .05 times 20. And let's suppose that otherwise we have it compounded monthly. So that means we have 12 compounding periods in a year. That gives us a future value of 10,000 times 1 plus. We're going to have to divide that 05 into 12 pieces. And then we're going to pay those 12 times 20 times. So this is 1 plus less than 0.5%, but it's going to be paid a lot more often. Okay, back to the calculator. Okay, calculator on, clear everything. So we have 10,000. Okay, times. In the first case, it was e, which is, I need to shift up from this key for the natural log. E raised to the .05 times 20. Okay. And I have an error there. Observe, I missed my .05. After all, this value here, 2 with 47 zeros after it, not to mention all the .688 and so forth, with 47 zeros after it, I believe that's more than the number of seconds since time began, billions of years ago. I need 10,000. So go back to this entry, and okay, now I need to insert a dot there. Press enter again, and I get something more reasonable, and this is pretty nice. My $10,000 in 20 years is going to be $27,000. That is what they call the magic of compound interest. And now I have 1 plus .05 divided into 12 little pieces, all to be paid out monthly. So my exponent is 12 times a year for 20 years. Okay, so we're talking a difference of $55. How important is that $55 to you? Well, it depends on how often you do this kind of thing. Many of you are business majors. If you have something to do with finance, that could be very important. Okay, I think that's the end of this part of our seminar.